Hello everyone. In this video, we will learn how to find the particular integral for differential equations. We'll start by understanding the theory of why we need to find a particular integral, and then we'll discuss how to find the assumed function, and we'll also discuss the special cases when the assumed function needs to be modified, and finally, we'll work through an example. Okay, so let's begin. So far, we have considered differential equations of this form, where we've got a second derivative, a first derivative, and a function of y, and where f of x would equal 0. So when f of x does equal 0, and the auxiliary equation has two distinct roots, when these a, b, and c values are taken from a differential equation, and let's say the roots are alpha and beta, then the general solution will be of the form y equals a times e to the power of alpha x plus b times e to the power of beta x, and we covered in a previous video on how to find these complementary functions. But when f of x does not equal 0, there must be a further term in the solution, which we'll call x. That makes the left-hand side equal to f of x instead of 0. So the complete solution will therefore be of the form y is equal to the complementary function, and y is equal to x, when this x is called the particular integral. So the general solution, or the complete solution, will be y is equal to the complementary function plus the particular integral. But if we think about this, we get y is equal to the complementary function, which means the left-hand side would equal 0. So we need to add on another term to make the left-hand side now go from 0 to f of x, where x is the term yet to be found. So the complete general solution to a non-homogeneous differential equation is given by the general solution is equal to the complementary function plus the particular integral. And to find the particular integral, we assume the general form of a function on the right-hand side of the equation, and determine the values of the constants by substitution in the whole equation and equating coefficients. So this will make a lot more sense as we work through an example in a minute. So for example, if f of x, the term on the right-hand side, equals a constant, then we assume y is equal to c. If a function on the right-hand side equals a linear term, or t of x, then we assume y is equal to a linear term plus a constant. If f of x is an x squared term, then we need to find the coefficient of x squared, the coefficient of x, and the constant, and so on for sine or cos, and for the exponential function, okay? And there are special cases. In some differential equations, the function on the right-hand side has the same form as one of the complementary functions. So for instance, if this is our complementary function, and this is the term on our right-hand side, you can see this e to the negative 2x appears on both. So in this case, the particular integral would not work, so it needs to be modified. And in general, if a function on the right-hand side has exactly the same form as one of the complementary functions, you multiply the assumed function by the independent variable. So in this case, we would assume this function, but would have to write y is equal to c x e to the x. So we've multiplied this by the independent variable. Okay, so like I said, this will make a lot more sense as we work through an example. And in example 1, we've been asked to find a particular integral for this function. So you can see on the right-hand side, we have a linear term. So we need to assume this function here. So we'll say, let y equal cx plus d. And when we find the values of c and d, and we have this equation for y, and then we find dy by dx, and then the second derivative, and substitute these three values into our differential equation, then we would make the left-hand side equal to the right-hand side. So dy by dx, well, when we differentiate cx plus d, the constant and the x term will go, So we're left with c. And when we differentiate this again, this constant term will go, so the second derivative will be equal to 0. So now we substitute each of these into this differential equation. So we get 0 plus 8 lots of c plus 16 lots of cx plus d. And this is equal to 8x plus 20. We'll expand the brackets out, so we get 8c plus 16cx plus 16d is equal to 8x plus 20. And now we'll equate coefficients. So this 16cx will map on to the 8x term, so therefore c must be equal to 1/2. And this 8c and 16d are constant terms, so they must be equal to 20. And we know this c is 1/2, so we get 4 plus 16d equals 20. So therefore d must equal 1. And now we can substitute these values of c and d back into our assumed function. So the particular integral will be y is equal to 1/2 of x plus 1. So if we were to substitute this back into our left-hand side, we would get 8x plus 20, okay? Well, I hope you found that helpful, and that's given you a clearer idea on how to find particular integrals for differential equations. If you did find that helpful, please hit the like and subscribe button below. And you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.